I love it when people bring their friends. This is great. We have some new faces, so we got to catch some people up for today. First of all, before we get into the story, any questions about any problems with Moodle, anything, final projects, you guys cooking up ideas, hopefully? I'm going to take that as a yes.
You have ideas, nothing actionable yet.
All right. Well, ideas are potentially actionable at least. All right. Yes.
Oh, I was just I thought we were gonna stop doing the videos.
Yeah, we're not. We did last week though. There's a couple more of them. I got confused. We did that last semester, but this semester there's still some videos, so keep at it.
Is there one for week 8?
I don't think for week 8 there's one.
Is there one for week 9?
9, 10, and there's like an exit video for the final week. Just check Moodle, guys. You should have everything there that you need. And of course the workshop assignments and the reading quizzes keep going. What else? All right, we are very close to the end of this train. So let's set the table here, especially we have a couple of new faces, like I said. So guys, what is at the heart of the story that's been unfolding beneath our feet all semester long? What is the central crisis at the heart of astrophysics and cosmology? Yeah, let's get some hands in the back. Yeah. No, you're all right, Evan. Go ahead. Yeah.
Liquid sun, baby.
Yeah. Tell me about that. What's that mean for people who are maybe new to the room right now?
It's just the great debate on whether or not the gaseous model of the sun, which is the standard, is incorrect, and if the suns more resemble a liquid state, like droplet.
Yeah.
Amongst other things.
Yeah, so for most of history, we treated the sun like it was some sort of condensed matter. So there was bonding, if you want to think of it that way. We didn't understand what bonds were originally, but then sometime in the 20th century, the sun was converted into a gaseous plasma. And that is proving not only difficult to reconcile with laboratory experiments, but it also unleashes some very strange stories about the heavens above us. So why does it matter? Who cares if we mistake the sun for a gas when it is, in fact, of a liquid state? How does it matter? Yeah, Zach.
Everyone cares because it changes our entire understanding of them, which also changes our understanding on how we want to do fusion on Earth.
Yeah, so you nailed two of the main reasons. One is it changes everything downstream of the lives and deaths of stars. Two is that we've been trying to do this new kind of power production on Earth, right? We've been trying for almost a century to create fusion reactors, which are wonderful because they're powered on hydrogen, which we can dig out of the ocean. It's everywhere. And it's clean. It's not a combustion product, so we can maybe look forward one day to not burning stuff to power our civilization. The problem is it isn't working out. And the reason it's not working out may be in some part because it's based on a mistaken understanding of how the sun does that magical process, right? And then, yeah, go ahead, Dante.
And then lastly, so things make sense.
Yeah, so things make sense, right? Somebody recently emailed me and said we should make for our podcast T-shirts that say "Making Sense Matters," but it is true actually. The story that we tell about the sky, somewhat preposterously and circuitously, feeds back into all of the scientific stories we tell about the natural world around us, which that would probably make more sense to people who took the last semester, because we looked at the solar system and we looked at the timescales that were given to tell the stories that we need to make the planets and everything else. They're incredibly short, and they're constrained by a cosmology which is based on these gaseous stars. And if we start to interpret the light from the stars differently, we might end up with a very different cosmological story that has a very, very different timeline. But kind of more importantly, like to your point, Dante, the things that we understand about how materials work on Earth is our best bet for understanding how they work, period. And if we treat the things in the sky like they're exceptions to the physics that we discover in our laboratories, then we have a terrible incongruity in our understanding of the natural worlds. And we're leaning towards this strange exceptionalism where, well, things don't have to necessarily square up with one another. And that's a really dangerous position for us to be in with respect to the central art form of rational discourse on Earth, which really is science, ultimately. Go ahead.
Yeah, I've heard a lot and there is truth to this, that the universe is, doesn't need to make sense to you. The universe has no reason to make sense to you, but you have every reason to make sense of it. It's your, like, as a human, that's like kind of your thing, is trying to make sense of it. So if you just say, well, it doesn't have to make sense, well then.
Yeah, how does that feed into all of our other socio-political dialogues, right? I can't tell you how many times I've heard people make nonsensical arguments in political, social, intellectual spaces and then say, yeah, but quantum physics doesn't make sense anyways, or, whatever. Pick your poison, right? People look to, whether they realize it or not, they subconsciously look to science, and specifically physics for some reason, because it's held as this incredibly mathematically rigorous domain, right? It's supposed to be some epitome of consistent, objective reasoning and logic. And I think that's ideally a good situation. The problem is if that stops making sense, then why should anybody bother making sense who has any authority on anything? It's kind of a slippery slope argument, but I think that it's valid, and it really, you can see the wobble in civilizations across time where they devolve into irrationality, often just prior to some really catastrophic transformations. So we want to avoid that, right? We want to have a physical science, a natural science that's internally consistent, and we want to live in a world that makes sense, because the alternative is dire, right? Okay, so that's kind of the scene that we've set so far with this course, and we obviously spent most of our time looking at the sun because it's the star closest to us. So, what is the most obvious piece that, just for people who are new, I know there's a couple new faces, so what's the most obvious thing that you might be able to explain to a 14-year-old about why the sun doesn't appear to be a gas? I'm not saying it doesn't have a gaseous atmosphere, but the surface of the sun, the light that comes from the surface of the sun, what is it about that? Go ahead, Kevin.
There's ripples.
The light from the surface, though. The actual light.
The light.
That is true, though. There are ripples. That is very difficult to explain. The transverse ripples as well. So there's a surface, is what you're pointing to.
Yeah.
Which is a good point, actually. But it's harder to see the surface with your bare eyes. But there's a pretty simple thing you could probably explain to someone in high school or something. Yeah.
The light from the sun is a full spectrum of light. But if you heat up a gas like hydrogen, you only get specific colors, specific shades.
Exactly.
Think like if you've ever seen this might not be the best example, like a neon lamp, like
Yeah.
they have specific colors.
Yeah. Pretty good
based on the
example.
gas that is in it.
Yeah, so if you hold up a prism or you spray a fire hose in front of one of those gas lamps, you're going to see individual lines of color splitting off. It'll kind of look psychedelic, like there's individual colors, right? You do that with, say, a heated tungsten filament, like an incandescent bulb, you get a rainbow, right? And of course, we all know that rainbows are a very naturally occurring phenomenon with respect to the sun's light. So the sun has this beautiful spectrum of light that we only see from heated liquids and solids on Earth in laboratories. And so in order to convert the sun into a gas, the past 100 years of astrophysics have had to cobble together all sorts of unrelated processes in order to try to approximate, in theory, that spectrum that we get very easily from heating up solids and liquids here on Earth. We get a very, very similar spectrum. So that's kind of where we started. Where have we been recently? So we've talked about this, we've kind of compared the two different stories of liquid stars, their lives and deaths, versus gaseous stars as they appear in your textbook, right? Where have we gotten to with that? Well, let's talk about let's not mess with the births of stars right now. Let's talk about how stars die, because we had basically gotten into these guys, these ultra compact objects last time. So, you guys help me review where we got to with this. How do these how do stars die in the standard model, in the standard gaseous star model? Evan, yeah.
They explode or they fizzle out.
Right? So does anybody remember the particulars of how that happens? Yeah.
They run out of hydrogen in their force diffuse, which eventually becomes more helium. And smaller stars, while with larger stars, it goes on to be various other elements until it can't fuse anymore.
Yeah, so they sort of, all of the fusion, all of the powering of the gaseous stars happens at their core. That's the only place where the temperature in these pressurized gas ball things would be high enough for there to be fusion. And of course, when the fusion runs out, because the fuel runs out, then it's thought that they essentially have no pressure to keep themselves, let's say, stable, and gravity takes over is the story, right? And it crushes these things into oblivion, different forms of oblivion depending on how big it is, right? So now, why is that not even a possibility with a liquid star? Guys in the back? Go ahead, man.
Because that entire idea relies on gases being theoretically infinitely compressible, but solids and liquids, condensed matter, can only be condensed to a point, and then it just will not condense any further.
Yeah, exactly. So perhaps surprisingly, the gaseous stars are built on ideal gas laws, which allow for indefinite compressibility. They also struggle to explain objects that appear to be hot and dim, right, under the gaseous model. The only way to make something hot and dim is to shrink its radius in the gaseous model, right? In a liquid object, or in any condensed matter, you can make something dim by just modifying the arrangement of the atoms inside of it, right? This is the diamond versus soot thing. They're both made out of pure carbon. They have very different bonding arrangements, and they have very different optical properties, right? You wouldn't propose to your new spouse with a ring of soot, probably, right? Although it'd be technically made out of the same thing. So you have very different ways to get dimness out of stars that have real structure in their surfaces. They can really rearrange themselves and appear quite different. Okay, so yeah, all of these stars are thought to explode and die in various ways in the standard model. In the liquid model, what happens to the stars for the most part? Left side of the room? Sleepy side of the room? What happens to the liquid stars? Evan.
They almost like evaporate, like how a droplet would in the air.
Yeah, go ahead.
They evaporate in the sense that they cool down.
Yeah.
They just go cold and dead.
Yeah.
Don't glow anymore.
Yeah.
But they don't evaporate in the sense that they disappear entirely.
Yeah. Well, yeah, maybe they have some rocky core. They've eaten a bunch of stuff over the years, so maybe there'll be something left over after a gazillion years. Looks maybe like a little kernel, maybe like a little moon or something. Okay, so yeah, they cool off. So this is a very different process. Now, in the standard model, all our stars have to explode. This is a little bit troubling because we don't see a lot of stars explode, right? We also don't see very many stars in those, compared to the stars on the main sequence, right? We see very few stars inside of these transition zones. So in the standard story, all the stars kind of swell up into these red giants. Then they go through these convulsions. They lose layers or whatever. They eventually collapse. Their cores collapse. You get the white dwarf phase. Maybe if it's a big star, you get something even crazier, which we're going to get into a bit more today. So, yeah, now I did bring up some kind of interesting stuff, though, and maybe we'll get back to this again today. We do see what appears to be a lot of stars not exploding, but doing what?
Disappearing.
Yeah, it's pretty crazy. So most people aren't aware of that. There's been a really big research consortium that has identified, um, several thousands of apparent stars that have just disappeared over the course of 30 years. And at least several hundreds of those cannot be explained in any shape and form other than stars disappearing, which is very strange. It doesn't fit into the standard textbook story, but it makes a ton of sense with a condensed matter star, actually, because the star essentially cools, the stars are essentially constantly being formed and they're constantly cooling off and going out of sight, right? This is a very, very different story that you end up telling as a result of these two paths, right? So, all right, any more thoughts on this dying stars standard model versus the liquid approach? Thoughts, concerns? Yeah, Kevin.
If stars don't go supernova, I'm sure we're gonna talk more about it later today, considering the subject. Um, how does the liquid model explain like pulsars and black holes? I guess black holes is what we're getting.
Yeah, we'll deal with black holes. I think we touched on pulsars a little bit last time.
Yeah.
Does anybody remember how? Well, let's talk about the two possibilities with pulsars in the gaseous versus liquid models of the stars. What's the standard gaseous explanation for pulsars? Does anybody remember? Yeah.
The gaseous model pretty much says that anything above, I think it's 3 times the mass of our star, 4 times.
Yeah, it's actually only 1.4. It's actually pretty small stuff. Yeah.
Anything over 1.4 times the mass of our star goes supernova, and the matter of the core pretty much becomes super condensed, and so the electrons are, I can't remember if they're like destroyed and like turned into like gamma rays and X rays and shot out, and that's how we detect the pulses.
Yeah.
Pulsars are, I mean, basically they're neutron stars that have beams going out of, I believe, their north and south poles, and they're rotating so fast,
That's the key.
several times per second. They're rotating, and that's why we get those flashes, is because
Yeah.
spinning so fast, and those points when that beam it's coming to face us, and then going away.
Yeah, critically, under the gaseous model, the neutron stars are these really hot, dim objects, right? And some of them appear to be pulsating in terms of their brightness is oscillating, sometimes on the order on second resolution, perhaps even faster. These things are spinning. And so the key there is that the only way to make a pulsating object using the gaseous model is to A, have its radius change. We saw this with the explanation for Cepheid variables. Or to spin the thing, right? Which is what they've gone with in the latter with the neutron stars. Go ahead.
I believe we also talked about specifically if it were spinning. We had discussed like the sort of questions around how it keeps itself together if it is rotating so violently fast.
Yeah, so it does. When you think about the size of these objects, even they're still on the order of the size of a planet, and you're talking about rotating this thing once a second, right? It does sort of boggle the mind how such a thing would maintain integrity. Of course, it's allegedly made out of some substance which we can't even possibly imagine examining here on Earth, and so, again, the exceptionalism comes to the rescue. How can we explain these rapidly pulsating bodies using a liquid model of stars, or a condensed matter version of stars? I think we talked about this briefly, yeah.
Like I could see it, if it were liquid, I could see it bulging. see it keeping its shape without making us.
But yeah, do you guys remember when we talked about turn signals?
Yeah.
Right? So in the liquid model, remember, a lot of the information we get about the light is reflective of the lattice, right? It's reflective of the bonding arrangement of the surface structure, right? This is the diamonds versus carbon thing, right? If you have oscillatory chemical processes or anything that is able to modify that lattice on a very fast time scale, then you have the ability for something to blink without actually rotating, right? This is in some sense analogous to how turn signals work. You build up capacitance in this system, it discharges periodically, builds up again, and you have a blinking light as a result of it. So there's very well understood condensed matter explanations for how you can get blinking without rotating a light. Now, people did actually make, police lights and stuff by rotating the lights at one point in time. There's much more efficient ways to do that, it turns out, just by manipulating the circuit, right? And so changing the lattice of a star would be very similar to manipulating the circuit in that analogy. Does that make sense?
Yeah.
Perhaps a little bit more boring than a super fast spinning neutron star, but nonetheless, perhaps more tenable as well. So, or perhaps not. You can make up your own mind. All right. So that kind of brings us up to where we are today, and we need to talk about this guy. This is, of course, the headline maker, right? So, yeah, Dr. DeLay, but we've got pictures of black holes. We know they must be there. All right. Well, we'll get to that. We'll look at this one in a second.
The lines that are drawn on the image.
Yeah, I was gonna say.
Yeah, it just
Last time I saw this, it was just blurry. Didn't have those streaks.
Pretty sure those lines are from. They just superimposed their simulation on top of it.
we'll go through it. We'll see exactly what they did. We're going to talk about it. There was actually, fortunately, a very prominent Japanese group that analyzed this paper after it came out and came to very different conclusions. All right, so the basic premise, though, of course, even with that image or with the concept of black holes, is that they gravitationally eat light, right? And at the end of last class, I sort of challenged the idea that light was affected by gravity at all, which is extremely heretical, but it's all kind of based on these deflections of starlight near the, originally it was based on our sun, and it's still to some extent, that's some of the most rigorous data that we have. The apparent position of light gets bent, and this was, of course, discovered primarily by Eddington during the eclipse in the early 20th century, during an eclipse in the early 20th century. What does anybody remember what I brought up as perhaps a challenge to this idea? Yeah, go ahead.
That outside of the range of the atmosphere of the sun, the corona, outside of that, the light doesn't bend, even though it should mathematically based on its gravity.
Yeah, it's kind of funny. So I came home from class last time after I think it's the last thing I presented to you guys, pretty much. And I was talking to my wife about this, and she's familiar with the work of the NASA scientist Edward Dowdy, who did this paper, which this chart comes from. And yeah, this illustrates the point, right? So, at different essential, radiuses out from the sun, there's a predicted Gaussian distribution through which the gravity should be affecting the light. The problem is that no one has ever actually observed optical deflection of light outside of the exact rim of the sun, essentially. So during that eclipse, it blotted out the sun. They could actually see starlights appearing through the flickers of the corona. They could see a star there, and its apparent position had changed, right? Now, turns out, so Dowdy, the guy who kind of did all this work, he unfortunately passed away very recently. He blamed this all on refraction. In other words, do you guys know what refraction is? Anybody? Oh, good. I'm glad that we did that. So you guys got to slow me down sometimes. So Refraction is that effect. Maybe you stick a pencil or in a half glass of water and you see it looks kind of bent, right? Light is bent. So gases can, of course, do this. You can see this density differences do this. If you ever go out on a hot day in the desert, you see these little mirages on the highway, right? This is kind of a similar effect of refraction. So while this table remains true in the optical, there has been reinforcement of this idea because people have been able to use radio signals to observe some sort of delay, actually, as radio signals pass, say, reflecting off of Mars, maybe as it's going behind the sun with respect to us or something like that. This is called Shapiro time delay. And these radio deflections are then reconverted, that delay is actually reconverted mathematically into an angular deflection. And so oftentimes, so I got home last time and my wife was like, oh no, like actually I was arguing with one of the chat bots or whatever about this, and it was like, no, we definitely measured the deflection outside of one solar radii. And I was like, I don't know about that. It turns out it's from like one of these radio signal measurements. And the question then becomes, how do you separate, not only do these radio telescopes measure some deflection, they actually measure a huge amount of refractive deflection. So refraction actually does something special, which gravitational lensing is not supposed to do. Refraction bends colors differently, okay? So they actually measure a huge amount of refractive bending near the sun. But they say we can factor that out because we measure at different frequencies and we can see that there's still a residual bending or time delay that's associated with it in these radio signals. And that residual is what we're calling the gravitational lensing. The problem is there's lots of other processes that can let's call it achromatically, without color distortion, can bend light. But guess what? They all involve condensed matter, right? And so if the corona of the sun is not just pure plasma, but actually contains any kind of particulate matter whatsoever, then all of a sudden you have access to scattering and diffractive and all sorts of processes that not only can bend the light with that residual amount, but they do it without warping the color. And they can also alter the path length of that signal, which gives you a time delay as a result of it. Yeah.
When you said plasma, you meant just gaseous plasma.
Exactly, sorry.
Yeah.
Yeah, that word plasma is really, really ill-defined. Of course, if you haven't figured that out by now, just about anything can be a plasma. Technically, even solid metals are plasmas. It's called a one-component plasma, if you want to read about it. It's a terrible, terrible word. But yeah, I'm talking about the gaseous plasma. So at any rate, there is a residual deflection. The question is it caused by gravity, or is it caused by condensed matter interacting with the light along its path of travel? That's to be stacked up against the rest of the story that we've been talking about this whole time. Yeah, in the back. Exactly. Well, there's some evidence that we do. Actually, we're quite sure that there's condensed matter reactions in the sun, which we can gain from the actual line spectra of chemical reactions happening in the corona. So we're pretty sure that there are actually condensed matter processes. Now, whether they're responsible for the residual deflection or whether the standard story of it being due to gravity, that again has to be weighed along with everything else that we're talking about here. But I'm personally unconvinced that gravity has anything to do with deflecting light whatsoever, mainly because I don't think light is a material body. I think it's actually an interaction amongst atoms, right? So, okay. So here, this is kind of interesting too. This kind of, I think, is important for sort of priming our discussion of black holes a bit more today, because one thing that we tend to forget is that You don't have to be that big of a star in the Standard Model to end up as a black hole, right? So, I often forget this too when I'm talking about black holes. I think, all this mass has crammed itself out of existence, right? These things aren't that big. They only have to be a couple of times the size of our sun in order to fit onto the landscape of black holes.
They don't even have to be double.
Not even double, yeah. So these aren't that big, right? So again, in the Standard Model, we see something that is really dim, but is pulling stuff around it, right? Now, does it have to be like pulling stuff really hard? No, it just has to be pulling it with the mass of 1.4 times our sun, right? And it's dim, and and that's essentially what we call a black hole. Now, there's this associated concept with black holes. So the idea with the black hole, of course, is that we've already moved past the white dwarf phase where we at least have an object, a conceivable material substance, if you want to call it that. It has a surface, at least, which is kind of how I define materials. Even, down past the white dwarf, even more stuff is gravitationally squishing it. You have a neutron star. It still has a surface, right? It still can be conceived of as a material body, at least, in some twisted sense. The black holes have crossed the threshold, right? And so at that, in this model, in this rendition of what's happening, there's so much stuff in one place that it literally breaks physics, and all of that matter is said to exist in a point of infinite density with zero volume. It's called a singularity, right? Now, what's up with singularities? What the heck is a singularity? Because, by the way, that word was in play long before black holes. Yeah.
Everything crammed into one little point.
It actually comes from mathematics and physical theory in general. It's actually a much bigger concept. That is what it means for black holes, though. That is the singularity we're talking about. But what's in general? What is this singularity? What does this mean? Anybody? I don't expect you guys to know this, but maybe you do. Yeah, Emmeline.
Maybe I'm just repeating it with different phrasing, but it has zero volume.
You're very close. So actually, a singularity is really pops up in any mathematical formula where something, essentially some term goes to infinity or some term is divided by zero and is therefore undefined. So you guys probably remember this from like math in middle school. If you divide something by zero, it stops making sense, right? So if you have all this matter, yeah, go ahead.
It's basically a mistake.
It's basic, yeah.
If you get a singularity, which is either you get get infinity, or you get a something that's completely undefined, then something in your either one of the terms, in your equation is wrong, like just ill-defined, or you were just messed up, or you messed up the calculation because something had to go wrong for the physics to stop making sense.
Yeah, so maybe instead of saying well, I do agree that if you try to apply your physical law where you shouldn't be, that it will stop making sense. But what it really means is that your model is broken down. So there's a very, very famous example of this from the early 20th century. Another singularity appeared, right? This one is kind of in some sense related to our black bodies studies from earlier, right? So, we've talked about how when you heat up bodies, you get this really nice line shape to it. It's called a black body curve, right? Or more generally, a Planckian curve named after Max Planck. Did a lot of the work on this radiative heat stuff. Well, the funny thing was, before Planck got his hands on things here, people were trying to model that light by applying classical electrodynamics to it. And the strangest thing kept happening. All of the mathematical models for how they understood light at the time resulted in this prediction over here on the right-hand side, where as you got to higher and higher frequencies, so shorter and shorter wavelengths, the energy, the intensity of the emission should go to infinity, actually. And this was a real nightmare because they knew that the light theory was good. They had lots of experimental data in the laboratory. They had made great mathematical models about light. And they also knew that when you heated up bodies, that they didn't have infinite quantities of ultraviolet radiation or gamma rays, right? They weren't just like burning your faces off just because you heated them up. But that's what the classical theory said should happen. So an infinity had appeared in the equation at lower wavelengths, right? This was called the ultraviolet catastrophe at the time because it was a real disaster. People didn't know what to do about it. Now, Max Planck actually, in some sense, he mathematically solved this problem. He did that by essentially realizing that light was transmitted in discrete actions from one atom to the next, right? You never just got the energy of light was absorbed in steps. This eventually led to the concept of the photon, which is, I'm not going to get in the weeds about right now. The point is that people had an understanding of light that was incomplete when they were trying to model the behavior of these heated bodies. And as soon as they adapted to the realization that light wasn't exactly what they thought it was, the formula was able to fit the black body curves perfectly after that, simply by quantizing the amount of energy possible from a ray of light, right? It was absorbed in whole steps, entire full waves, essentially, right? Okay, so singularities happen. They usually mean that we misunderstand something. I would say they almost always mean we misunderstand something, but at the bare minimum, they mean that our theory no longer fits the world we're trying to map with it, which is really, really critical. Now, this hasn't been lost on the black hole scientists. So, there's a number of these guys, some of the early pioneers of black holes who have kind of rebelled in their old age against the idea that these singularities are real physical phenomenon, right? So Roy Kerr is one of the famous examples, but there's just a lot of these guys. Problem is they're basically retired at this point. They kind of step out for these pop sci pieces every once in a while, but they don't have a lot of sway in the field anymore. But the idea that singularities point to something wrong with the model is probably the much more sane way to approach this stuff. So let's talk about what sorts of evidence people are trying to pin on these black holes. Unlike the ultraviolet catastrophe, where it was pretty obvious to everybody that these heated bodies weren't emitting infinite quantities of radiation in the ultraviolet and gamma ray and X-rays, right? That was kind of obvious. When it comes to black holes, people see weird stuff in the sky and they say that that is evidence for the black holes. So what are some of those things that they see? I think we've kind of pointed to maybe the most obvious one, which is that there's places where stars are orbiting something that you can't see. It's so dim you can't see it. What's even worse is sometimes you can see it, but it's super, super hot, actually. Like so hot, it's only emitting really, really blue light, otherwise known as X-rays, right? Now, again, with a gaseous star, the only way to make something hot and dim is to shrink its radius, right? With a condensed matter approach to stars, you can make something that is hot quite dim by simply altering its lattice, right? So again, most of these objects aren't that big. They're basically a little bit bigger than our sun. So the orbital dynamics we see aren't some insane behemoth thing that's ripping their neighbors apart. It's just a star that appears to be really, really dim. Sometimes hot enough that we can, sometimes not so dim that we can't see the hot X-rays coming from it, right? A couple other pieces though. We talked about this pulsar stuff. Gravitational waves. You guys ever heard of these things? This was a Nobel Prize a couple years ago. So this is another point where people claim to observe these black hole entities, right? So does anyone know how this works? How do they do this? Yeah.
can't remember specifics, but there's something in the textbook about these laboratories being built in like 2010s, I believe, and uh they pretty much had really, 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 really sensitive like lasers
Yeah.
in an L formation as you have there, and they pretty much had to uh very finely detect like s- very slight movements of the light um in so with I, I I can't remember how they um dealt with like surround sound of light and vibrations of the earth, all that.
Yeah, let's walk through it. So the basic principle, right? This actually falls out kind of I honestly kind of like the idea from a materials perspective, right? So we've talked about light a bit more, and we've kind of wrestled with, what the heck is light a little bit. Um, certainly, certainly it's evident that light is transmitting some information, but what kind of information? Well, it's actually telling one atom is actually dissipating electric action to the next atom, right? Now, we've talked about why people don't really think about this being a physical process anymore. And it has a lot to do, of course, with the lost popularity of ether models, right? But the current field conception really isn't so different, and we can map it onto something like a mediator very easily. And in any case, it makes a lot of sense that if atoms are connected to one another physically, that the deformations that we associate with light would also modify the tension of that medium as well, right, in a very reflexive way. And so Einstein, his mathematics, and also just quantum electrodynamics and basically the most precise models we have of light, they also give us this idea that there is a similar wave that is, in some sense, very, very much like light, except it's instead of light, which gives us a little bit of a push, this has a relaxing effect, which draws bodies together. We call them gravitational waves. Just like light, they're transverse oscillations of whatever medium. You can call it a field if you want. I don't care. But it's very, very similar to light, except opposite in terms of its momentum, right? So the idea is that, okay, well, if there's these huge events happening that are great energetic disturbances, they're going to send ripples out, which can be measured gravitationally. And so people built these devices that Kevin was talking about. They're called interferometers. The basic idea is that like you said, you put these lasers in a situation. You have a beam splitter, so it's a two-way mirror essentially, and you allow the light to go through and come back, and it interferes with itself. And if there's any disturbance to either one of those arms of it, then the light waves will get out of phase by the time they come back to the detector, right? And so you should, in principle, be able to measure really, really tiny differences. And so what they did is they put these on two different sides of, basically on two sides of the world. I think it was actually in America, on two sides of America. But regardless, say you separate them quite a bit. So you say, if they have the same disturbance occurring at two places on Earth, then it's likely that that's not something local, right? It's not like a truck drove by or something like that and disturbed the arms. It's something more global, right? Then what they do, so they go looking for that. They go looking for correlations between the disturbances that they see in these interferometers at two very different locations. Okay, go ahead.
I believe they are building more now.
Oh, I'm sure they are. There's quite a few, actually.
At least.
Yeah. Yeah, it's a very popular method. By the way, this interferometry stuff is useful for lots of things other than gravitational waves, but that's a different story. A lot of the radio telescopes, the stuff I was talking about earlier with the time delay relay studies are interferometry based as well, which they're basically just looking at path length differences in a signal's travel and how it interferes. It's kind of beyond the scope of what we have time for. But okay, so you find some signals that are correlated between your very distant detectors, and you say, this isn't a truck driving by. Great. Now, how do you know that it's actually a celestial signal? Any ideas? Yeah. So one thing you could do, and this actually is the most promising approach, is sometimes those mergers that you're looking for, that you're trying to correlate to these waves that are arriving at you, sometimes they do have visible, or not visible, but sometimes these black holes, like I said, they're not completely black, right? They actually have some radiation visible in the X-ray, right? So you might actually be able to see something happening. I mean, you can't see X-rays, but you have detectors that can. And you can correlate the travel path and the location with what you're observing here. That's actually become that's become a very that's not always possible, but it has been done in recent times, which actually lends some credence to the fact that they're actually measuring something celestial. Go ahead.
Can you put one orbiting Earth, like in space?
Yes, but tricky. Very tricky. It's very hard to keep things stable out there. But that is possible, and there have been some interferometry-based telescopes in space. There's one called ALMA you can read about. What they did originally at the time that these black hole mergers, neutron star mergers, were first allegedly detected by this LIGO project, which, by the way, was an enormous multi-billion-dollar multinational experiment. What they actually did was they made an enormous library of possible celestial events and what their signals should look like here on Earth. So they populated essentially a huge spreadsheet with hundreds of thousands of different possible events and what they're in the sky that could be expected, let's say. And they went looking for one of them inside of their data set. Now, that's a little bit of a sketchy enterprise when it comes to experimenting, right? So, I forget, anybody ever play with synthesizers here? A little bit? Anybody ever make a tone out of a white noise pattern before? Right? So this is kind of a fun thing to do, actually. If you just take a noise generator and then you filter it, you take out all the frequencies except one, and you amplify that frequency, then you can get any notes out of the piano just from a white noise source, right? You can basically find, like, white noise by definition, definition is just an assemblage of a bunch of different possibilities, right? So you can find whatever you're looking for if you filter it hard enough. And so there was some sort of suspicion that this may have been a huge filtering operation for the first few years. Like I said, there have been a few of these in recent times that have been correlated to actual X-ray sources. And so there might be something to it after all. So again, the merging of stars, so the collision of stars, that's not particularly challenging for the liquid model either, right? Because sure, these bodies may actually merge sometimes. In fact, with liquids, it's actually quite sensible for droplets to merge. That would actually make a lot of sense. So yeah, like you were saying, to date, I think this is the picture, I don't know if this is the one from your textbook or not, but there's been a ton of these different detection events, right? And of course, based on how big the objects are, we either separate them as neutron stars or black holes, yeah.
Yeah, with gases, like gaseous stars shouldn't be able to merge, right? Because gases just want to go bounce off each other.
I mean, it's hard to say what these things even are. I agree, but they're not even gases anymore. I mean, they're just these sort of outrageous states of matter that are, sort of concocted to fit the observations rather than having any basis in laboratory science or anything, right? It's not like we've ever made a ultra compact object here on Earth before, right? So who knows? They can do whatever the theorists want them to do, unfortunately. So, all of this is to say that, it seems like they might be measuring something celestial with these gravitational wave detectors. at least in some of the cases of it. I don't know if in that many of the cases of it, but in some of them, you actually do seem to be able to correlate it to observational data about the sky and its position. Now, whether those are exceptions and it's just a big filtering experiment with a white noise generator, history will have to decide in the future. But this is, in some sense, the most precise and perhaps the most well-defended evidence that people will point to for these black hole thingies actually existing. Again, it's not really a challenge to the liquid model either. I think it kind of fits with either one, and we've seen this happen a few times along the way. So, I don't know, thoughts, questions about this before we move on to this guy? What do you think? Gravitational waves, LIGO, interferometers. All right, let's keep going. All right, so
I know it's been more than 1 year now.
yeah, when was this? I should have written it down. We have a date up there. No, I think this is in 2022.
4 years ago.
Yeah, it's been a while. Gosh, time flies. So, you know, this was a really interesting moment. So, you know, a lot of these, like I said, early black hole scientists coming out, yeah, this is, you know, we made a mistake, perhaps. This doesn't make a lot of sense. Singularities don't really occur in nature. The LIGO stuff happens. Like I said, it's still ambiguous. It doesn't really argue for ultra-dense objects. It just argues for the gravitational influence of high-energy like mergers of dim bodies in space, right? But this, now we have a picture of a black hole, right? So it's got to be a real thing all of a sudden, right? All right, so this picture actually was a joint project between 200 different universities in 20 countries. And they were imaging a galaxy which is 54 million light years away. And this is the final product of the image that they produce, right? So, like I said, almost immediately after this came out, yeah, go ahead, Kevin.
I was just looking it up. It was like last quarter of the 2010s. So 2017 was when it's taken, and the final image was like processed and released in 2019.
19, all right, there you go.
I remember when that image like came out and just having two very different reactions from people I knew. Basically, it was either those who were scientists being like, "Hold your horses, guys! Hold your horses! We don't know what it is," and then all the non-science were going like, "We have a picture of a black hole. You can't deny it now."
Yeah, I was there too. Yeah, I roll in circles where most of the people I was hanging around were like, "This is we need to look at how this was done because somebody's cooking the books here." All right, and well, let's talk about so this Japanese team. They reanalyzed it. This is the paper. If you want to get into the nitty-gritties of it, I believe I threw it up on Moodle. So, you know, there's a couple of things. First of all, they reanalyzed the data themselves, and they tried desperately to recapitulate this ring structure that was shown, and they couldn't do it for the life of them. They also found something a little bit disturbing, which was that the signal-to-noise ratio of the detector in this system was 1. Now, what does that mean exactly? It means that for every piece of data, there's one piece of garbage, right? So, generally speaking, that would be a completely unusable system for imaging something like the bones in your hand or something, right? You would actually not be able to see anything approximating the bones in your hand. You would just see a big mush if you were doing X-ray imaging of your hands with a signal-to-noise ratio of 1, right? So this is very troubling right away. Things got even weirder, though, the deeper they got into the data of this paper. They actually found that the final image was constructed by using essentially 1 pixel point per billion. So they filtered out 999,999,999 pixels for every one that they decided to keep. The final What's that?
What was that billion thing?
Well, it was a filtering operation, so they only kept one data point per billion that they took from their actual sensors. So this final image construction, they used the equivalent of they call 3D pixels because they get depth information from this. They call them voxels. They actually only used 6 voxels out of the entire data set to reconstruct that ring structure that we saw on the first slide, that picture. It's actually from 6 pixels, although the final image has a resolution of 1,000 pixels, voxels, let's say, to be precise. So how do they end up multiplying by several orders of magnitude the precision of that? Well, it's not pretty. Yeah, go ahead.
I'm gonna say they probably like saw something of a ring and just like blurred it.
No, they install no ring whatsoever. So basically what it came down to, how do you filter, right? So what does it mean to filter? What does it mean to throw data out, right? So this is a really, really sketchy process that you'll learn about if you ever do any laboratory science, right? Because what does it mean to throw data out when you do an experiment? You do an experiment, let's say, I don't know, give me an experiment, somebody.
Rockets.
Let's say I want to figure out what the average height of everybody in this room is or something like that. Oh, in the back. Yeah, we're going to throw out some of them, right? But why? I want to get my goal is to figure out, let's say, what the average height of the students is in this room, right? Now, I might be able to throw out some of the data points because I measure a couple of people and, I don't know, my tape measure was not working or something. Or
It wasn't long enough.
it wasn't long enough. That's a good one. Yeah, it wasn't tall enough. So I was like, I can't use these data. I can't use these students. They can leave, right? Now, the problem is if you do too much of this, and sometimes it is justified to filter out data, right? Sometimes you can make that justification. Actually, a huge part of setting up experimental systems is trimming out all of the fat so you can focus on the piece of the puzzle you're interested in. This is certainly what these scientists would argue that they did. They said, well, we don't care about that data, we don't care about that data. The problem is that if I threw out 999,999,999 students and I had one left and I said, this is the average height of the students in the class, nobody would believe me. In fact, I probably wouldn't have a job anymore if I was putting out that kind of science, right?
You probably could be put into some kind of
Yeah.
society.
Probably be locked up, yeah. I certainly wouldn't be publishing in journals anymore.
You'd be put in the white room with the rats.
Right. So this is what that galaxy actually looks like when you take an optical image at the highest resolution possible, right? The real interferometry picture looks like the one at the far back up there. Best case scenario with this interferometer at 43 gigahertz, you get that picture that's up at the center. And then you basically throw away all of the data except for the couple pieces you want. You use a bunch of Gaussian smoothing algorithms and which you could just think of as Photoshop, and you get your very nice ring structure down at the bottom, which nobody other than you could produce because they didn't understand your motivations. Is it any surprise that this picture happens to look exactly like the picture of the black hole from the movie Interstellar, which came out right before this? I don't think so. Right, so this is what people expected a black hole to look like, and of course they found it. Now, humans are really good at this kind of thing in general, by the way. So like,
Confirmation bias.
yeah, you guys ever look at like the stump of a tree and see a face in it or something like that, right? Yeah, yeah. We're really good at this, actually. What's that?
Pattern recognition.
Yeah, yeah. Does anybody know what this is called when you see faces and stuff, where there aren't actually faces? It's called pareidolia. Pareidolia. But you can imagine that pareidolia is not that big of a problem because you look at the tree stump, you see a face, and you're like, well, it's not actually a face, that's fine. But what if you really did expect to see faces in trees? might be able to find enough trees to actually support your theory, actually. So this is pretty bad science, honestly. I don't even know if it actually qualifies as science. And this is exactly sort of the problem with having well, the problem is with things that don't make sense, and then people doubling down on them not making sense, and then being convinced that they can find things that support their world that doesn't make sense as well. This gets into really sticky territory because, again, 200 different universities, incredible mathematics, dump trucks full of hard drives to process all of this data, right? These are really smart people doing really sophisticated transformational algorithms on this data. The problem is they knew what they wanted it to look like before they started. That's really the problem, okay? That's really a really big problem with experimental science in general, and it's gotten lots of people in trouble over the years because they kind of tailor their experiments to give them the conclusions that they want. And it's very, very hard to avoid this, actually, even if you are a person of high integrity, because you come to the table designing your experiments in some sense loaded with an understanding that you hope to demonstrate. Go ahead.
So pretty much, they I lost you by that.
Yeah.
I mean, I just thought about how you were talking a couple weeks ago about that this like satellite or something to prove the sun is a liquid. Even then, like you have something that a theory that you're like, I'm certain this is what it is.
Yeah.
I'm going to go and prove it.
Yeah. Yeah, it's a problem. I mean, it's actually kind of funny because the guy who's basically funding that project, he's already convinced the sun's liquid. He actually doesn't care, right, if we prove it or not. Actually, I hate the word proof in science. Proof is good for mathematics because all a proof is it says that you followed your axioms true to form and you processed an argument that's logical outcome of your axioms, right? In science, the best thing we can do is show that what we see is consistent with everything else. So that's kind of the closest we can get. We can basically rule out things that can't be true, but we can never really say that anything is absolutely, certainly the case in this theoretical space. Go ahead.
I was gonna say is they pretty much went into it with the mentality of we aren't leaving with nothing.
Yeah, I mean, think about it. You have 200 universities spend billions of dollars on something. You better get something good out of it, right? So, like with our satellite project, that we're trying to build a satellite to, well, for starters, to get a better picture of the surface of the sun than anyone's ever done before. But in some sense, that's really the mission, right? Now, if what we see reinforces the conclusion that the surface of the sun is a real surface and that there is actually a liquid condensed surface there, great. If it shows that that is not the case, that's great too. But the mission of being able to make a really high resolution picture of the sun is a cool project all by itself, actually. And whatever we learn from it will be quite interesting and beautiful, I'm sure. So, not to mention all of the technology that results from that because, space drones and stuff, right? So, all right. So there it is. Yeah.
I thought about this too. When with the Event Horizon telescope, which isn't actually one single telescope, I thought about this comparison to like an over budgeted movie or just any project with way too many people, just way too many cooks in the kitchen.
Yep.
At a certain point, communication's gonna falter, and at some point, how do you get 20 countries to cooperate well enough for that system to actually be accurate enough for you to call it science?
Yeah. Well, it's also like, look at how preloaded it is. It's called the Event Horizon Telescope, right?
Yeah.
All right, so, and this is funny, when we had our powwow in San Francisco a few weeks ago about this this satellite to the sun, we're very much like, there's no way in hell we're calling this the liquid sun telescope, right? Because we're just gonna try to make a picture of this thing. And we can, people from our group even can write papers arguing that it's evidence of condensed matter. Somebody else can use that data and argue completely oppositely that it's evidence of gaseous stars. If they find that useful, then they're welcome to do that. So, yeah, I mean, I think what you're saying is a really good point, Dante. Like, if you have this enormous bucket of money and all these institutions working on something, and the name of the project tells you what the final outcome is going to be, I mean, good luck finding anything else, honestly. It's hard to imagine that the Event Horizon Telescope will not find an event horizon. All right. So, all right, let's kind of recap this. It's kind of three fundamental open questions here with respect to the black holes. Does gravity actually bend light? Or does it have, or are these differences in travel paths something closer to the other processes which bend light on Earth, in the laboratory, in this glass of water, right? Are there refractive, diffractive, scattering, absorption, emission processes amongst the condensed matter that are accounting for the bending of light that is hailed as proof that gravity bends light? So that's the first open question. Does gravity actually bend light? Because if it doesn't, the entire black hole story makes no sense all of a sudden. 2, black holes have negative heat capacity, which is something that is a violation of every conservation law that we would test in the laboratory. What does that mean? It means that as the black holes are heated, compressed, they actually get colder.
What's it called?
It's called negative heat capacity is the technical term for it, right? So it doesn't click very well. So again, it's this hallmark of exceptionalism, right? It's, well, yeah, we would never see that in a laboratory, but these things are special because they're huge and far away. They're actually not that huge, though, as it turns out.
Is that just science space packing?
It's not. That's kind of the point of this class, right? The point of this class is 100 years of space magic is enough in some sense, right? And you might say it doesn't matter, because who cares? But
I care if all my money's going to it.
well,
Yeah.
yeah, there is some money going to it, but I think actually the consequences are much worse than that. I think it really has to do.
That's easier to convince people.
Yeah, I mean, there's some argument for that, but that sort of saddens me because I think that in a really healthy civilization, we would spend a lot of money investigating how nature works. The difference would be that we wouldn't tolerate inconsistencies in our explanations that resulted from that. If we saw things that didn't make sense, let's say singularities like the ultraviolet catastrophe, we would say, hey, we need to go back to the books and understand light better because we're clearly missing something really important here, which is what they did. Now, the story from light is far from over, but there was a huge leap in our understanding, right? And so, yeah, we really want to have a science that's internally consistent. We want to have a situation where physics doesn't just stop working sometimes. That's troubling. And then to double down on it and say, no, it's pretty cool that physics stops working. That's just borderline terrifying to me, honestly, because I really think that it permits some of the scariest people that have ever existed to do the things that they do when they convince an entire population that the world doesn't have to make sense. I don't know if you guys ever read The Emperor's New Clothes when you were kids at all, but it happens a lot. It happens in really, really despotic, terrifying ways, right? The Maoist revolution that starved 60 million people to death, you know? These kind of...
It's over 100.
Yeah, maybe hundreds of millions of people die from these really charismatic idiots who convince the populations that things don't have to make sense. You guys can stop farming food and melt down all of your kettles to make ore so that we can build more metal stuff. That's what everybody should be doing. That's what Mao did, right? That's an idiotic idea, but It was so compelling, and people had completely surrendered their will and the need for things to make sense, right? And it's not just Mao. The same thing happened in Nazi Germany. The same thing happened in Pinochet's Chile. It happens all over the place, and it's really, really bad. And it really worries me. It really worries me that we think that that could never happen to us, but it really could happen to us actually. And the first step to making sure it doesn't is that making sense matters, right? Go ahead.
I think it'd be good to go into like seeing physics breakdown is cool, but why?
Yeah.
Like, why does it break down, and how does it change?
Absolutely. I actually think all the places where it doesn't make sense are completely exciting mysteries and fertile ground for progress and renaissance, right? Those are wonderful places, and it's a funny thing they don't really teach you when you go to train to be a scientist. You should be looking for those things that make no sense, because that's what you're going to make a career on. That's how you're actually going to make breakthroughs, is you're going to find those things that don't make sense, and you're going to make them make sense. Yeah.
Well, I think the problem is that rather than saying, "Hey, this thing doesn't make sense yet," because we don't know because we don't understand it, they're saying, "Oh yeah, that just doesn't make sense." Period.
And it's cool.
It's cool that it doesn't
Yeah.
make sense because I like that I can do whatever I want with it.
That's right. That's right. Yeah. So
You said there were 3 things, but
oh yeah, right. So I guess the third one is just this question of what a singularity means when you encounter it in your theory of nature. What happens when your mathematical model introduces an infinity or divides something by 0? What does that tell you, right? Of course, the popular interpretation is that tells you, hey, cool, this is a place where the universe stops making sense, right? But that's not a very healthy way to model reality, I think. It's much, much more healthy to say, all right, I think we've got something that we don't understand that's going on here, right? I think that our formula has ceased to capture the nuances of reality, right? So, it's gravity bend light. What's up with the thermodynamics where physics breaks down? And what's up with what does the singularity really mean for us? These are all really important questions in determining what these actual events that we see in the sky, these dim gravitational bodies, what the heck is actually going on with those? All right. So there are some actual sane possibilities, by the way, that have been kind of kicked around along the way. I thought maybe I would enumerate some of these. These are actually quite adjacent to the standard liquid story, right? So I've already thrown out to you guys that the most sensible explanation from a condensed matter perspective for what the heck these black holes and neutron stars and stuff are is that they're just sort of cooled off stars, right? They don't even have to be that big. They're just dim, right? So there's some the standard models have entertained some of these ideas. The only problem, of course, is that they have to veer into really extreme circumstances, because why? Yeah.
time scale.
Time scale, exactly. So in other words, in order to cool off something naturally, so for our star to actually cool off to the point that it's not even glowing anymore, that it looks something like a brown dwarf or a Jupiter, that would take a very, very, very long time. Now,
Trillions of years, right?
I mean, depends how close it is, yeah. Presumably they're blinking out all the time, right? Under the liquid model. This Vasco study with the disappearing stars would point to this is happening all the time. So they're on a continuum. But yeah, the problem is that the standard cosmology, which is kind of where our course turns to for the last 3 lectures that we have, we're going to get into cosmology. The standard cosmology we have is called the Big Bang cosmology. The Big Bang cosmology has concluded that the universe itself is a mere 13.8 billion of years old, which seems like a long time. But if you consider, that life appeared only a few billions of years ago on Earth, and presumably the Earth was here before that, It's basically yesterday in cosmological timescales that the universe was alleged to have been born. Therefore, there hasn't been enough time for stars to actually cool off and go dim and black and have this appearance, right? So, you know, there's been some different papers published across the years where these different black hole phenomenon, neutron star, well, more the black holes than the neutron stars, have been modeled as various exotic forms of cold, dead matter. They're not, of course, going so far as to saying they're cooled off stars necessarily. So, you know, it's very close. It's very close at hand. And I think that the final constraint is going to be how much time we have to make all of this happen, which is kind of where we're heading next. So the two biggest pieces of this puzzle, which we'll get into Thursday, we're going to start cracking into. There's two real pieces of the Big Bang story. One has to do with this idea of the universe which appears to be expanding. We'll talk about why people think the universe is expanding, and we'll think about whether that is actually the case. The other thing is this afterglow of the Big Bang, which is called the cosmic microwave background radiation. These two pieces are essentially the backbone of the cosmology that constrains our timelines to just a few billions of years, right? Particularly this expansion idea, because the way, of course, you might be wondering, how in the world do we know how old the universe is? Well, the basic idea is that if the thing started in an explosion of sorts, let's just simplify it that way, that if we see how fast all the pieces are moving away from where the grenade went off, that we can back calculate the timeline to where it all started at. Yeah, go ahead, Kevin.
What is our like kind of point of like the center of the universe?
Well, so it's kind of expanding. In theory, it's expanding in all directions.
Well, like it is okay, so it's expanding in all directions, but where did the Big Bang happen in this theory?
Well,
Because like if it's here, then why is it here?
Well, the only reason I was pointing down was because the center of our universe is Earth, and the extent to which we see the oldest things we see in any direction is the same, basically, in all directions. And that's would be true from any point in space. If you went to a different star, you would look out in space, and you would have, and again, everything would appear to be around you, like you would appear to be the center of the universe.
yeah, it's kind of expanding from everywhere all at once in this story. But I think that the question you're asking is a little bit akin to what would it feel like to stand on top of a black hole? And I would probably say, are you sure that black holes are what you think they are? So I think what we have to do next time is really go back in the history books to the 1920s and see why in the world people think that the universe is expanding. Because, well, that's where we'll start on Thursday.
I wasn't even talking about expanding the universe, just the simple fact that it will always appear to be around the universe, will always appear to be orbiting around you in some way.
That is true, but we'll have to look at the specifics of why people even think that. So anyways, have a good week, guys. We'll see you on Thursday.